Hey everybody, it's time to get into Lecture 8, which is all about describing quantitative data with numbers. So we can get around and having to graph things for at least a little while. Our EQ for today is really a big idea that is assessed a bunch on the AP test, and that is which measures of center should be used with which measures of spread whenever you're describing quantitative data. So let's get some background information first. We always want to describe a population. Parameters are what describe a population. Okay, these are numbers. Getting information from all individuals, though, is difficult. So what we do is we get information from a sample to speak for that population. And those are statistics. You see, generally the most useful statistics are summary statistics because these are the statistics that describe a sample in ways that we are interested in. So summary statistics are information from a sample that describes the center and spread of that sample. Let's take a pause and take a look at some notation. And the first one is all about proportion. We have different notation for dealing with parameters and statistics, and these are going to come into huge play when we get into more advanced statistics later on. So for proportion that describes the entire population, we use lowercase p. Now, some fancier older textbooks might use the Greek letter pi, but we tend to know that from 3.14159. So in general, you just want to use the letter P, lowercase, whenever we are describing the population proportion. Okay? Remember proportion, this is where we're talking about percentage of individuals that might take on a certain value. When we're talking about the proportion from just a sample of individuals, we're going to be looking at this, and it's called P hat. Not fat, but P hat is how we pronounce this guy. Okay? Now, when we're talking about the mean of all individuals in a population, sometimes this is known as the true mean. The true mean, we are going to use the Greek letter mu. So the true mean will be this guy. Kind of looks like an M, kind of looks like a U. It's neither of them. It's the Greek letter mu. I'll even try and make that a little bit nicer. Just like that. Okay? And that we pronounce as such, mu. You might also hear it as moo, so make the cat or the cow. I don't care, whichever you do it. When we're talking about a sample mean, the average of just a small sample of a population, it's an X with a bar on top, and uncreatively we read that as X bar. Okay? The median. So our median is going to actually get the short end of the stick here. It doesn't have any notation, so we're just going to kind of put a cross there. You just write it as the median, and you can preface it as population median or the sample median. It doesn't really matter. There's no notation there. Standard deviation, however, does have notation, and that is this. It is not O. It's not a cursive O. It is another Greek letter, and that is lowercase sigma. You might remember uppercase sigma. That's the summation notation. We don't want to mess with that. We're looking at lowercase sigma if we're talking about the population standard deviation. Okay? And then if we are talking about the standard deviation from just a small sample, we use the letter S. Sometimes we use S sub X. The X is tiny and it's below the line, so we read that as subscript, S sub X. Okay? So this is just one of our measures of spread that we will talk about. We've got a few others. And then we have our two measures of center. We want to make sure we understand the notation of those because you're going to use it a lot. Now, let's go ahead and discuss our measures of center. Remember that our measures of center should always be describing the typical value of a distribution. It's not always the middle or the visible center of the distribution. You got to unwrap your head around that a little bit. Why do we care about the measure of center so much? Well, if we're looking at just a sample, then that measurement can help us make accurate predictions about the population. Okay, it's one value that speaks for everybody, and that's a really, really powerful value if it's accurate. Okay, so the two different measures of center we use are the mean and the median. The mean is not resistant to outliers, but the median is resistant to outliers. What do we mean? Let's actually take a look at a brief example to try and describe that. Let's imagine you have a modest shoe collection, okay? Now that modest shoe collection may include a $45 pair of shoes, a $50 pair of shoes, and a $55 pair of shoes, okay? And let's even kind of consider this on an x-axis somewhere, right? So we've got one pair of each. Now, the mean of your entire population of shoes is pretty simple. Add all of those up and divide by 3, and we end up with $50. That's our mean. Okay, the median, however, is that going to be any different? Well, remember that the median is always the middle value. So the middle value in this case is indeed still $50. So what we want to notice here is this is a symmetrical distribution, and the mean and median are actually identical to each other. In any distribution that is truly perfectly symmetrical, meaning it's the same shape going straight down the line, same folded in half, the mean and the median are located at the exact same spot. They are the same value, and it's right in the visible center of that distribution. Okay? But now, what happens if I decide I'm going to have a treat yourself day? Right? And I decide I'm going to go big, and I'm going to get myself a nice like $200 pair of Jordans. Okay? Now, what's happened to my new mean and my new median? Well, my new mean, when I include this $200 pair of shoes, we've got our $45, 50, 55 plus 200, and we got to divide all those by 4. My new mean is going to be $82.50. Compare that new mean to the old mean. It's drastically different, right? What happens to the median? The median is still going to represent the middle value, okay? So the median of that value, or of our distribution of shoes now, what we want to try and do is start crossing off your lowest and then your highest pair. And then you want to get down to the middle value. Well, here, whenever we've got two middle values, there is no middle value, right? So if we have two middle values, what we want to do is take the average of these two. And what's the average of $50 and $55? It is $52.50. Okay? So if we have an average of $52 or a median of $52.50, notice the disparity in our two measurements of center. Which is the more reliable predictor here? Which is the more accurate predictor of, like, what's your typical pair of shoe? And in this case, the median is by far a better predictor of what is a true typical pair of shoes in my closet. Now, what we want to notice here is that this would be like a right skewed distribution, because most of our values are on the left-hand side, and we've got one weird tail off to the right. So in a right skewed distribution, what we'll find is the median is always going to be closer to the hump over here, but then your mean is going to be pulled all the way over to the tail. And what we can see in this case is that our median is less than our mean. In any right skewed distribution, the median is less than the mean every single time. What does that mean for a left skewed distribution? Well, a left skewed distribution is just going to be the exact opposite shape. So let's go ahead and take a look at that opposite shape and see if we can't figure it out based on the definition that we just described. Our median is still going to be somewhere closer to the largest hump here, and then our mean is going to be pulled toward the tail. And in this case, the mean is further on the left-hand side of the axis. That's going to be closer to the minimum. So what that tells me is that our mean is now less than the median, and the relationship has changed for a left skewed distribution. Okay? This is a very, very, very common question that is assessed in multiple ways on AP tests. What's the relationship between the mean and the median based on its shape? Or if you can see that you have two mean and median that are almost identical to each other, you know it's going to be a symmetrical distribution. If your mean happens to be smaller than your median, however, that's going to tell you that, hey, it looks like I have a skewed left distribution. One thing we can always know to remember this is that the mean is always going to be pulled toward the tail in a skewed distribution. Okay? That's a good verbal way to summarize it. Your mean is always pulled toward the tail. And the way that I remember this, I think about my kids. I've got a couple of cats at home, and I've got a 5-year-old and an 8-year-old. And when they were babies, what did they want to do to those cats? They would want to pull on the tail of my cats. What do we always have to tell them? It's mean to pull the tail. So always remember, it's mean to pull the tail, and you will always know where the mean is in relationship to the rest of your distribution. If you do have a symmetrical distribution, however, your mean and median are almost always going to be identical. Now, let's go ahead and move on to measures of spread. Before we can get into measures of spread, we really need to address a few special measures of location. Now, we'll get into more of these in a little bit later on lecture, but one measure of location is known as a percentile. And what that does is it describes the percentage of individuals that are at or below a specific individual. This is important when we are trying to describe a few special locations, and those are the quartiles, right? If you look at the root of these words for quartiles, quartile 1, quartile 2, and quartile 3. 3 quarters would be 75% or 75 cents. 2 quarters would be 50 cents. 1 quarter would be 25 cents. So that's an easy way to help us remember the quartiles. Another special fact is that quartile 2, that 50th percentile by definition, is the middle value, and that's your median, okay? Now, one way that we can start to identify where each of these are in a distribution, especially if you've got all of your information, is you can start, again, crossing off lowest to highest. So let's do that when we look at this one, the commute times of a few people in New York in minutes. How long does it take them to get to work? Well, we start off by looking at our lowest value, highest value, and cross it off. Lowest, highest, 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 lowest, highest. And now we're left with 2 individual values. The person with 20 minutes and 25 minutes are our middle 2. So our median, in this case, is going to be the halfway point between those, and that's 22.5. That's our median commute time. Okay, minutes. Now, how do we find the first quartile? Well, what we do is pretty simple, is now we look at the first half and we do the same thing. We look at lowest to highest. Don't include the median though. Lowest, highest, lowest, highest, lowest, highest, lowest, highest, and now we have the halfway mark between 15 and 15 minutes. Well, that's easy enough. That's 15 minutes. Okay, do the same thing to find the third quartile, but do it with the upper half. Lowest, highest, lowest, highest, lowest, highest, lowest, highest. Halfway in between 40 and 45 minutes gives me 42.5 minutes. Now, why are these quartiles so important to our measures of spread? Well, what we are looking at is how each individual relates to each other, okay? Measures of spread are measures that will help you make precise predictions about a population. The smaller your measurement of spread, the more consistent your predictions will be about a population. Okay, if you have a very large spread, then what you're going to be doing is you're going to be making widely varying predictions about a population just based on some sampled data. Okay, so we need to decide which ones are going to be the best tools in our measures of spread tool chest. First one is range. Now, range, unfortunately, is really widely resistant to outliers. If you go back and you look at our previous example of shoes, here, before I had my treat myself day, I had a range of $10, just max minus min, 55 minus 45. Then, when I bought those new pair of shoes, my range increased by a substantial amount. Okay, now my range is $155, drastically different. So, the range is heavily influenced by outliers, and what that tells us is the range is not resistant to outliers. It is going to change when we introduce outliers. So we don't want to use it by itself, especially for skewed distributions. You can talk about the range, but don't let that be your only measurement of spread. The measurement of spread we really want to use for any skewed distribution like this is what's known as the IQR, the interquartile range. And it's Q3 minus Q1 every single time. The third quartile minus the first quartile, because those are the inside quartiles. They're just inside the min and max, okay? So in our example, what was our min and max? Let's find out. Q3 minus Q1, we have 42.5 minus 15 gives us an IQR of 27.5 minutes. So what that tells me is that the middle 50% of all individuals in this set varied by 27.5 minutes in their commute time. So what these are is these talk about the most typical individuals and how much they vary from each other, okay? The nice thing about these is that outliers do not affect IQR. So what does that tell us? The IQR is a resistant measure, and we like resistant measures. We don't like things to be influenced by outliers because we know the outliers are weird. We don't want to be influenced by weirdness, Okay? What's another measurement of spread? That's called standard deviation. Okay, standard deviation, this is a really tough one for students, and we'll go over this more in detail in class. But standard deviation is the average distance a randomly selected individual is from the mean. This is a weird, wordy definition. Not only that, but it says average in the word twice. Okay? It has the average distance from the mean, and we know the mean is the average. So more on this later. But here's what we want to understand. Since sigma, standard deviation, remember that's our notation for standard deviation. It's sigma or S sub x, either one of those. It has mean in the definition. Well, since mean was not a resistant measure to outliers, standard deviation is not a resistant measure to outliers either. Okay? Let's go ahead and jot that down to the left-hand side here. Mu and sigma are not resistant to outliers. What that tells me is that these two measurements should always go together every single time. Okay? Now, what about the other two that we looked at? Median and IQR. Well, neither of those were resistant to outliers. So, I'm sorry, they are resistant to outliers. So median and IQR are resistant to outliers. So what that tells me is that these two should always go together. And it makes sense too, because hey, how did we find IQR? We found IQR by looking at Q3 and Q1. Well, how did we find Q3 and Q1? We had to go based off of the median. So these two, median and IQR, should always be used together. Mean and standard deviation, they should always be used together. Okay? Now, the last thing that we want to be able to describe is unusuals. Okay? So how do we calculate any unusuals? Well, we want to look for outliers. One way we can do that is with the IQR, and that's with the 1.5 times IQR rule. We have to do two calculations for this. And what we can find is that if an individual is more than 1.5 times the IQR more than Q3, it's going to be an outlier. Or if an individual is more than 1.5 times less than Q1, that's going to be an outlier. So that means we look at the upper and the lower end, the minimum and the maximum. We look in both of those directions. Let's go ahead and do that here. Okay? In our example, our IQR was 27.5 minutes. 1.5 times that IQR is going to give us 41.25. So we take that 1.5 times the IQR and we add to that quartile 3. So 41.25 plus my quartile 3. My quartile 3 was up here. That was my 42.5 minutes. And that's going to give me 83.75 minutes. My question is, did I have any individuals that had a longer commute time than 83.75 minutes? And we'd say, yes. That person that had an 85-minute commute time is an outlier by the 1.5 IQR rule, because 85 is more than 83.75. Now, we want to look at the lower side too. So now what we do is we start with Q1, and our Q1, if we go back up and look, our Q1 was 15 minutes. That was our first quartile. So we have 15 minutes minus 1.5 times the IQR minus the 41.25 calculation that we did before. And when we subtract those two, we end up with actually something that doesn't make a whole ton of sense. We end up with, what, negative 26.25 minutes? How can you have a negative commute time? Nobody has a negative commute time, which means we don't have any individuals with a commute time that is less than this, which means we have no outliers on the low end. The only outlier we have is this one at the upper end. Now, this is not the only way to calculate outliers. If you're dealing with a symmetrical distribution, you can use this rule too, by using standard deviation, and that's the, if any individual is more than 2 standard deviations above or below the mean, then they would be considered an outlier. Let's go ahead and calculate this just to see how it would work and see if we have the same kind of outcome, if we end up finding any outliers in this distribution. Okay, so we start off with the mean. Now the mean of this distribution, I had to calculate this using a one variable stats calculator like you find in our class website, and the mean was 31.25 minutes. The standard deviation was 21.87 minutes. Okay, so we interpret this term here as meaning on average, a randomly selected individual will be 21.87 minutes away from 31.25 minutes. That seems a little bit weird. Again, we'll talk more about what standard deviation means, but for right now, let's go ahead and try and calculate this outlier. Okay, so we start off by doing 31.25 plus or minus 2 times that standard deviation, 21.87. Punching this into my calculator, I get negative 12.49 minutes when I do the subtraction, when I do 31.25 minus 2 times 21.87. But if I add 31.25 plus 2 times 21.87, I end up with 74.99 minutes. And so what I want to do is, this is like my lower boundary for an outlier, and this is my upper boundary for an outlier, similar to what I found in this previous example of negative 26.25 and 83.75. Okay, so let's go ahead and figure it out. Do we have any individuals that are more extreme than these two outside of this range? Well, I obviously don't have anybody that's less than negative 12-minute commute time, but I do have my 85-minute individual that is more than my upper bound. So we get the exact same result by doing this calculation. You generally don't want to do this kind of calculation, however, if ever you are working with a skewed distribution. You want to stick with 1.5 IQR rule. So this is going to be for skewed. This is going to be for symmetrical. Now, can you use the 1.5 IQR rule for symmetrical distributions? Absolutely. It's totally fine. Okay? The last thing that we want to look at is how can we summarize everything, right? That's the whole point of what SUX does, is it's supposed to summarize your distribution. Well, we can do that with numbers, and that is called the 5-number summary. Okay? The 5-number summary describes the center and spread of a distribution all in 1 or 5 numbers by using the minimum, the quartile 1, the median, the quartile 3, and the maximum. So let's go ahead and write out our 5-number summary from this distribution. We had a minimum commute time of 5 minutes. The quartile 1 was 15 minutes. The median we found was 22.5. Quartile 3 was 42.5. And then our maximum was 85. So what this shows me here is where the center is. I can find the center pretty easily by looking at the median, and I can say to myself, well, how close is the median? Is the median in the middle of 5 and 85? I would say no, it's actually a lot closer to the minimum. And if my median is a lot closer to my minimum, that tells me my distribution is probably skewed right because of that relationship. If my median were actually closer to my maximum, I would end up with a skewed left distribution. Again, we'll have a lot of chances to practice this, so don't worry about it right now. Let's look lastly at a box and whisker plot, because that is just a natural extension of the 5-number summary. All we do with the box and whisker plot is we graph that 5-number summary. So I'm going to start off with an x-axis that goes from 0 all the way up to maybe 90 or 100. And I'll go ahead and go by tens. And we'll count that's 20, that's 40, that's 60, that's 80, and that's 100 minutes. Okay? What we can find is that we had our minimum. We're going to make a mark there. We'll make a mark at our maximum. We'll make a mark at Q1 that's a little bit bigger. We'll make a mark at our median that's a little bit bigger. And we'll make a mark at our Q3 that's a little bit bigger. The box connects Q1 all the way to Q3. Then we connect to make our whiskers. and that's a box and whisker plot. What we tend to do, though, is make a modified box and whisker plot. So we don't, if we happen to have any outliers, we don't extend the whisker all the way. What we do is we leave a special mark for any outliers, and then our next highest value that is not an outlier is where the whisker ends. Where was my next highest commute time before 85 minutes? It was 65 minutes, and that is where my whisker ends. And this is our box and whisker plot. We'll practice graphing those a lot more in the coming days and on your practice. For now, this is going to get you enough to be able to do your practice 5 assignment. Thank you guys so much for watching. Come ready to class with questions. Have a wonderful day.